Hi and welcome back to the lab. Today here on the bench we have an ICOM IC-7300 and the radio has problem which its power amplifier. So we have different power levels on the different bands, and that is very interesting because the owner has told me that on the 14 megahertz 20 meter band we have approximately full power, but on the other bands, so for instance on 80 meter it is only 10-12 watt maximum output power, and that sounds to be a very interesting problem. So let's go right to the bench and let's look into it. Alright, and here we have our radio, and what the owner told us is completely right. So we have here on the 20 meter band approximately 90 watt, and when we go down here to the 80 meter band it is really only maximum 20 watt. So and that is different on all the different bands, so that is not normal, and we really need to investigate it. Okay, and let's look how it looks like here on our LP500. So the radio is on the 80 meter band, and here audio, and that is definitely full power. And let me go over to the 20 meter band, which we have here, and 1 2 1 2 1 2, and you see it is peaking over 90 watt, so that looks like more or less normal, even if I would say 80 watt is a little bit too low. But when we go down here to our radio, so you see that it is really set to maximum power, so we have 100% set here our power. So let me go to FM to do here a double check. So when we now go back here to our LP500, so let's see with the carrier, it is 85 watt. And when we go down here to 80 meter band and switch it to FM as well, so that is maximum. And that is definitely something totally wrong. So let's really go here into it and let's see what's going on. Alright, and here we have our radio open. So here on the right hand side we have our power amplifier, and here our output filter, and here is our RF unit, and well, then on the other side we have our main board, and we have our tuner unit. And what I want to do right now is to go by the elimination process. So that means let's check if we are able to take a part out of our circuit. So for instance here our tuner, which also it is looped, so it is normally not automatically switched in, but we just want to take it completely out of the circuit, and we try if without the entire board, if then maybe our output power is back good. Because, you know, that is a kind of funny problem we are facing here. I mean, if an amplifier is able to deliver 85 or maybe 90 watt on 20 meter, but it is not able to deliver even only 20 watt on 80 meter, that means that it is not it is not subsequently the amplifier itself. So it could be potentially that there is something wrong with the filtering, because you know we have here all the little relays and they switch the different bands, and if something would be wrong here, that could be a reason that it is working on one band and not on the other. The same with the antenna tuner circuit, which could lead to the same problem. But well, on the other hand, there is a potential chance that there is still something wrong with our amplifier itself, but we need to start somewhere, and so we start what could be done at easiest, and therefore we go and eliminate first parts of the circuit which we then can be sure that they are not involved in the problem. Okay, so we have here our antenna connector, so that means here is the input to the tuner, so that means this cable goes to the PA, and I pull it out and I put here an adapter to the unit, and now we can connect our dummy directly to the PA if we like, and now we can start the radio and can see what it does. Alright, so radio is set to the 80 meter band FM, and let's see, and yes, so we have our 13.7 watt as we know it, and that is not good. Even we have now disconnected our complete circuit. Now let's go over to the 20 meter band FM, and still 85 watt. That means it is definitely not our tuner, so let's go ahead. Well, what we could check next is if the level on the different bands are more or less equal, which they should. So we get from our RF board the input towards our power amplifier, and that is this cable here, which is delivering the drive signal, if you like, into our power amplifier. And we want to check if the signal here is always the same level on the different bands. So that is what we do next. Right, so I've already prepared it. So you see that is here the TX line from our RF unit, and we are picking the driving signal, as I already said. And I want to know if the signal is everywhere the same level. So let's go and check it. So we start here on the 20 meter band, and then we go through our different bands, and we watch the output from the RF unit. Okay, so you see the meter, so our level meter, which works with the test that I am using here, 2 gigahertz, and so we can see what it means on 20 meter. Now here I go and press my PTT, and you see we producing minus 4.8 dBm. So that is drive level on 20 meter, and we know that that was good for 85 watt. So we should have at least on the different bands the same level. If not, that means that something is wrong here in our driver circuit, because, as I said, it should be always approximately the same. So let's go down to 80 meter. Now I've switched it to the 80 meter band, and let's see what we see on the 80 meter band. And that is minus 5.5, so that is not a huge difference. Minus 5.5. Let's go back to the 20 meter. Minus 4.8. So that is not a huge difference. So that is more or less the same level. So let me go up to the 10 meter band, which is dialed in now, and here it is even stronger. It is minus 2.6, but even with 2.6 we are not able to reach 100 watt. So now on the 10 meter band, to verify it, so it is 69 watt, which a much higher level. So I mean, we know that normally as higher the frequency, as less amplification we have, so that is known. So normally we see with the lowest frequency on let's say 160 meter or on 80 meter, we see the strongest signal, and as higher the frequency it goes down. But here we see we have 70 watt output power with yeah, as I said, a higher drive level, what we have seen. And if we go for instance to 160 meter, and you see on 160 meter we have a little bit higher output power than on, let's go to the 80 meter. That is even as you see less. That is a little bit funny. Okay, conclusion out of that is clearly that we have more or less the same drive level. The difference maybe around 1 dB, which I would call normal. But you see that we have different PA output levels. So that means that the fault is most likely more here on our PA unit, maybe the output filtering or driver or whatever. So we need to dive a little bit deeper here into our circuit to get a better understanding what's going on here. Okay, and the next what we check first are our voltages. So here we have our power amplifier transistors, MOSFET, and let's see what we have. And you can see here the voltage. So that is just fine. We have our 13.7 supply voltage, no problem. Let's see what we have at our driver. Where is it? There. It is 13.7 as well. And then we have our little pre-drivers here. And they are, according to our service manual, at 9 volt. Okay. So let's go and check our pre-drivers. 9 volt, that is fine, and that one is at 9 volt as well. So voltages are fine. So next will be to check our bias voltage, which we find at the gate of our both power amplifier transistors or finals, whatever. So let's see what we have there. When we touch it, we see nothing. So we have, of course, to press PTT, and then we get, what is it, 585. on, let me go back to 14 megahertz. Okay, so let me check it here, because that is what is referenced in the service manual, and that is, as we can see it, 1 volt, so that makes sense. 1 volt, so that is a normal bias voltage, so it is always between 1 volt and 2 volt, so it depends, but 1 volt is just fine. Now let's go over to the second final transistor. And what is that? And that is definitely not right. So we have 7 volt as a bias, so that is wrong. Let me go back on the 80 meter band just to compare it. Here we have 0.8, which is more or less okay, and here we have 13 volt, and that, you know, is definitely wrong. So remember, if we give such a high bias level to a transistor, that means that it really opens it up, which means that we have current flow, and that means an incoming sine. So our signal, what we want to amplify, cannot do something to you know, the transistor, because it is already completely open, or now open, you call it different. Yeah, the switch is closed, if you like, and a high current is already going through our transistor, and that means it would not 13 volt. That means it would not amplify. So that is the point. But where do we get 13 volt from? So that is absolutely not clear. Here must be something wrong. Okay, so we need to have a closer look to our PA unit, which we have here, and we need to enlarge it here a little bit, that we all can see what's going on. So here we see our finals, and what we see as well is here our power line. So we get here over our transformer our 13.7 volt to each of our both finals, and then what we can see as well is that we get here over this both diodes our bias voltage to individually to each of our both amplifier transistors. So you see it here. If we go and follow this line here, you see that it is going directly to the gate. Okay, and well, this voltage here is coming from a digital analog converter, which we have on the main unit. So let me zoom in here a little bit, that you can see what I mean. So we have here our digital analog converter. So we get from the processor the information on which level our power amplifier gates should be, and then you see here two analog out 1. Maybe I have to do it a little bit more here. So analog 1 and analog 2, and if we follow it, we see that that is the idle voltage, HF idle voltage 1 and 2, and of course this goes directly to an impedance converter, so that are this both operational amplifiers. So we see here HFID2 and HFID1, which is our bias voltage, which goes then here directly out over to the PA board, and it will then go directly to our amplifier gates. Okay? That means we should see at least our voltage on both, on the D301 and the 302. So we should hear our 1.2, 1.5, whatever volt, which then set the bias voltage to the amplifier transistors. And that is what we need to check here on the board once again to understand what we get here. That is now the next what we want to see. Okay, and once again our first gate, and that is at 0.8, so 800 millivolt, which is fine. And now I go directly over to the second, which is on 13.2, which is totally wrong, of course. Now let me see. So the diodes are really small. So let me go to the cathode on the first here on the right hand side, and that is on 1.2, so that makes sense because we have here two resistors, and on the other transistor we already have at the cathode, let's see, our 13.4 volt, which is definitely wrong. So let me see here on that side, what do we have on the anode of our diode. So let me see, 1.9. So that is definitely right. So that is a voltage coming from our digital analog converter, and that makes sense, because over our diode would mean another drop of 0.7, 0.5, 0.7 volts, then the both resistors in front of the gate, which would then mean that the voltage at each of the gates is more or less the same. But we see that we have on the cathode our 13 volt. Once again, there we have it, and that is funny. That is completely funny. Okay, back to the schematic. So we see here that we have 13.4 volt, which we have as well at the gate. And you see we have here two resistors in front, so that is where we have a small voltage drop, so that is what we have seen as well. And we have seen that on the anode here of our diode we have our 1.9 volt, which makes sense with the normal voltage drop over the diode and then the voltage drop over our both resistors. So the question right now is, where do we get our 13 volt from? I mean, we cannot get it here from our driver transistor, whatever. I mean, it is isolated here by our transformer, so there is no way to pass through. Then we have here our both capacitors, which would block DC, so that is not possible. Then our 13 volt, what we have, of course, at our transistors, but normally this 13 volt could not be seen at the gate. that would mean that there is a potential leak from, you know, here to the gate. So therefore it would be a drain gate leakage or breakthrough. And that is funny because obviously it is not completely a short or whatever. I mean, short, there is no path to ground, so we wouldn't see, no, there is definitely no path to ground if there is a drain gate leakage. That means from here to there. Only if it would be a drain to source breakthrough, then we would see a short going here to ground, which is obviously not given, but it seems that there is, for any reason, a path here, you know, to the gate, which is completely funny, and well, that is something we need to investigate a little bit more. Okay, and making a long story short, so everything was pointing to the finals. So as you already see, I have taken out both finals because in any way, if something is wrong with the finals, you have to change both. It is always a risk to leave only one in, which seems to be okay, so that is definitely wrong. So if you ever have a problem with the final stage, change both. And then look what we have here. Alright, as you can see here, so that here is our suspect final connected to the tester. And now let's start here our test routine. And I hope you can see it. The field effect MOSFET FET is identified as 2 diodes. So we do it once again, and you definitely see that is a faulty one. And because there are still 2 diodes which are working in a way, that is obviously the reason why we don't get a full short. So therefore that was a funny behavior we have seen. But anyways, let us connect the second one to the tester as well, to see how that turns out. So that is always a little bit fiddly here. Alright, oops, alright. Now they should be connected. Let's see what we get. And yes, so have a look. So that is definitely the proof. So our amplifier was constantly running on one final transistor, which causes that we see the funny behavior on the different bands. And at least we didn't get full power out. So that is exactly what I thought. So once again, let's check it a second time, and you see it is definitely identified as MOSFET, and you see everything is fine with the second one. But what we definitely do not know is if because of the malfunction, is there something already, you know, hit inside the now obviously shown transistor, or is there something maybe already wrong? So it is never ever a good idea to only replace one if you feel the other one is fine. So I really recommend to replace both, and that is what I will do here. By the way, I have updated the firmware to the latest version, so we are now at version 1.4. So that is done as well already. So now I have to order these final transistors, because I do not have these types on stock. There we have it. No, I haven't those on stock, so I have to order them, and then we will go ahead. Okay, so it's now 2 days later, and you see the new transistors arrived. Well, in a little bit funny bag, and I wonder, and at the same time hope that it is ESD safe, because these transistors are ESD sensitive, so I hope that really the bag is fine. Alright, so let's go ahead and let's fit here our new transistors into the radio. Okay, so the first what we have done is we have cleaned all the pads so that the new transistors will fit in a perfect way. And now we put on some heat grease, and then we can go ahead. Alright, so thermal compound is applied here to the heatsink. And now we have to put back the transistors anew. And of course, we really have to watch out for orientation, since we have here on this side it is gate, and that is drain. And so we really need to see that we get it first time right. And an important thing you see here on the board as well is that we have here an indication that there is a notch, and notch is what we have on our transistors as well. So if we watch here our new transistor, which we have down here, so you see that there is a notch on the left hand side as well, which is indicating the drain, and therefore that is what we need to do. Our new transistors are now in place, and now you might think that we easily could solder them in, but you never should do that. Because it is very important that you first put your screws here into the holes, and then the transistor gets aligned, and then you can solder it. Because if you do it the other way around, you have potentially the transistor not really in place, which means you will have stress on you know, the pins and the board itself, so that is never a good idea. So now the next what I do, I put here this little shield with the screws over it where it has to go anyways, and that means that the transistor is then optimal in place, and then I start soldering. Okay, now you see what I mean. The shielding here and the screws are now in place, and the screws are tightened, and now we really can start the process of soldering. Okay, so let me show you how I do it. So I show you one solder point, and then you got an idea how I'm doing it. So I've done enough flux here to our joints, And now let's see that we get it right. And that is, as you see, the whole process. I will do it now, of course, for the other leads as well, but that is boring. You've seen how I can do it, and let me now do it for the other leads as well, and then it is finished. So soldering is finished, and you see the result. So that is how it is done. Now I have to clean the joints, and then we can go ahead. Okay, so I think we can do a first test. So I've already set again here the radio to the 80 meter band and to FM. We know that here we only had, what was it, 14 watt or so. I have reduced here my RF power to 13% just to start gently. And well, let's see what we have. So with 13%, I'm not sure if you can see the meter over there. So that is 13%, and we have 13 watt. So let me increase it to 45, 43. And let's go a little bit higher. Let's say 70%, and it is already almost 70 watt. So, you know, that already shows that it is obviously back working. But we have put in new finals. And remember, when we have to replace a final pair, then we have to align the bias current. Bias voltage, bias current, but at least it is a current, because both transistors have to be in idle mode on, you know, the same current, that both transistors are working equal. And therefore, before we go ahead and before we start stressing the radio again in a daily business, we really need to take care on the right setting. So let me prepare the setting, and I show you the procedure, and then I hope everything is back fine and working. Okay, setting the idle current is with this model an entirely microprocessor operated process. So it is not as it was in the past, that we had a little pot where we adjusted the current, or the later, maybe the IC-7000, that was already processor operated, but you still have to go into the menu, and you have to connect your amp meter, and then you start the process, and you adjusted the right current here with our wheel, with our main wheel. So with the new generation here, everything is completely and entirely microprocessor operated. So you do not adjust anything, you do not put your amp meter to the circuit, and therefore you really have to rely to, you know, the firmware and the processor. And that is the reason why I really refreshed to the latest firmware, which is the 1.4 version. I do that, or I have done that, because, you know, it is known that the IC-7300 is suffering from faulty finals. And because that is what it is, if, you know, the program, so the firmware is not 100% working perfectly, then you definitely have the risk that, you know, the BIOS adjustment is not done in a proper way, and that means that potentially your transistors can fail. And I hope that really with now the latest software version, it is now fine. And I would recommend, because we do not have any deeper information, so we do not have an information that they have worked on the process of you know, doing the idle setting, so the BIOS setting, if they have done anything to the firmware, but I think that could have been done. We don't know, and we do not have any information. So what I would do with any of those radios, I would first put the new software, the new firmware in, so the 1.4 version, and secondly, I would do it then, so the adjustment of the BIOS, I would do it with any radio, even if you do not have replaced your finals, just in case that something was wrong with the earlier firmware versions. So that is my view. So you can have a totally different view, and you can put your thoughts on that under the video. But that is what I would recommend. Okay, so now let's start the process. So we have a jack, the service jack in our remote jack. Now we have to press menu and function together, and then we start the radio. You see 1.4 here, by the way. And now you see we are in adjustment mode. Very important is that you have a dummy load connected to the radio, what we have, because we have done here our first test. So that is given, because when we start the process, then the radio starts transmitting, because the radio needs or the sensors needs the information what the current is, and therefore you have to have a dummy load connected to the radio, otherwise you are jeopardizing your final, so don't do that. Okay, so now next step is we have to touch here to TXID, so that is the next what we have to do. Okay, and according to our service manual, we have now to touch ID, and now we are setting here VDL IDL set, and that will be started by pressing here our set button, and then we should be able to go to the process. So that is then here our first step. Now, so that is done. You have seen it has switched to TX. Now the next one, again here TX ID idle setting, is final ID set, which is the next one, and we again have to press set. You see now it is on TX, and now final one needs to get adjusted, and we say set. You see that here it is adjusting it, and then we go to final 2 set, and we see we have here exactly the same. The next is now driver set, idle current set, and that is again reached by the set button. It is now in transmit, and we have to start here our process. You see it is running, and now we are done here with our idle setting. So now we would be already in a transmitting power set, which we do not need to do. So that is a different story. So in our idling carring adjustment, our driver idle setting was the last one we really had to do. So therefore we are done with our bias or idle current adjustments. Okay, so I hope I have arranged it that we really can see everything. So I'm on 80 meter, which was the problem, and I'm on SSB, so let's fire it up. Audio, audio, and we have 107 watt. I hope it is visible once again. 1, 2, hola, audio. So that is working, as you can see. Let me go back here to FM once again, and you can see it. We have 95 watt, so that is fine. Final is already heating up a little bit. Let's see what we have on 160 meter. Audio, audio. So it is over 100, very nice. 7. Audio, 105 watt. 14 meter, no, not 14 meter, 14 megahertz, 20 meter. Audio, 100 watt, no problem. And let's go to 18 megahertz. Audio, 100 watt, no problem. And 21 megahertz. Audio, 104, no problem. 24 megahertz. Audio, 100 watt, no problem. And 28 audio, audio, and it is 99, peaking 100. So now everything is really back to normal, and that is a repair we can call a success. Everything is really back working, and radio can go back to its owner. Alright, so thanks for watching, and catch you next time. Bye.